Right now, at this exact moment, two machines built by human hands in the 1970s are flying through territory that nothing from Earth has ever touched before. They're moving at 35,000 miles per hour. They are so far away that a radio signal traveling at the speed of light takes nearly 24 hours to reach one of them. And in April 2026, NASA engineers made a decision that sent a chill through the entire space science community. They turned off one of the last remaining instruments in Voyager 1, not because the instrument broke, not because the mission was ending, but because Voyager 1 is losing power so fast, so quietly, so relentlessly, that engineers had to choose between killing the instrument deliberately or risking the entire spacecraft shutting itself down in a panic. That sacrifice bought time for something NASA is now calling the Big Bang, an ambitious, high-risk engineering maneuver that could determine whether these probes keep talking to us through the 2030s or go permanently silent within the next few years. But here is what nobody is talking about loudly enough. While all of this is happening, Voyager is still finding things out there. Things that do not fit our models. Things that are genuinely reshaping what scientists believe about the space between the stars. The universe beyond our solar system is not empty, it is not quiet, and it is not behaving the way anyone expected. This is the story of what Voyager discovered, what it is discovering right now, and why what it found in interstellar space is one of the most unsettling and extraordinary things in the history of space exploration. To understand what makes the Voyager story so remarkable right now, in 2026, you have to go back to where it started. September 1977. Two spacecraft launched within weeks of each other, not because NASA was planning an interstellar mission, but because of a rare alignment of the outer planets that only occurs once every 175 years. This alignment allowed a spacecraft to use the gravity of one planet to slingshot to the next, visiting Jupiter, Saturn, Uranus, and Neptune in a single grand tour. The window was open. NASA took it. Both probes were designed with a 5-year lifespan. They were expected to do their planetary flybys and then drift silently into space, their transmitters long dead, their instruments frozen. Nobody seriously planned for what happened next. Voyager 1 completed its planetary work by 1980. Voyager 2 finished its planetary tour in 1989 with a legendary flyby of Neptune, the first and still the only close-up look any spacecraft has ever taken of that distant ice giant. After that, both probes were pointed outward, away from the sun, away from every known planet, into the dark. And they kept going, and kept going, and kept transmitting. Year after year, decade after decade, generation after generation of scientists sitting in the same control room at NASA's Jet Propulsion Laboratory in California, listening to whispers from machines that should have been silent long ago. Voyager 1 is currently about 15.8 billion miles from Earth. Voyager 2 is roughly 13 billion miles out. These numbers are so large they are essentially meaningless to the human brain, so consider them this way. Light from the sun reaches Earth in about 8 minutes. A signal from Voyager 1, traveling at the same speed as light, takes almost 24 hours. By November 15th, 2026, Voyager 1 will reach exactly 1 light day from Earth, becoming the first human-made object in history to cross that boundary. 1 full day for a signal to arrive. Another full day for any response to get back. If something goes wrong with Voyager 1 at that distance, NASA has to wait 48 hours just to know if their fix worked. The loneliness and the silence of that distance are difficult to put into words. But the probes are still out there, still moving, still measuring. And what they are measuring is changing everything. Let's talk about the power situation first, because this is the ticking clock underneath everything else. Both Voyager probes run on radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium-238 into electricity. They are elegant pieces of engineering, producing power with no moving parts, no solar panels, no fuel to burn. But plutonium-238 has a half-life of about 88 years, and the generators have been running since 1977. As of April 2026, Voyager 1's generators are producing less than half of the power they had at launch. The decline is steady, predictable, and unstoppable, losing roughly 4 watts per year. 4 watts sounds tiny, but when your entire spacecraft runs on barely enough electricity to power a dim light bulb, 4 watts per year is the difference between science and silence. To manage this decline, NASA engineers have been doing something like triage on a patient who is slowly running out of blood. They have been turning things off one by one, sacrificing instruments and systems to keep the most critical functions alive. Heaters, cameras, scientific instruments, all powered down over the years to extend the mission. On April 17, 2026, engineers sent a command from California that took nearly 23 hours to reach Voyager 1. That command deactivated the low-energy charged particles experiment known as the LECP, an instrument that had been running almost continuously since the probe launched in 1977, nearly 49 years without rest. The LECP measured ions, electrons, and cosmic rays in interstellar space, mapping the invisible pressure fronts and particle density changes in the region beyond our sun's influence. Losing it is a genuine scientific loss, but the alternative was worse. Just weeks earlier, in late February 2026, Voyager 1 experienced an unexpected drop in power during a routine maneuver. The spacecraft came dangerously close to triggering its automatic fault protection system, a self-preservation mode that would have shut down critical systems and required a risky, multi-day recovery process. Engineers shut down the LECP to keep that from happening, to buy time. The time they are buying is for the Big Bang. This is NASA's nickname for a complex engineering maneuver that has never been attempted before on a spacecraft this old, this far away, or this close to dying. The plan involves simultaneously switching off several powered devices and replacing them with lower power alternatives, a careful reorganization of the spacecraft's energy budget, designed to free up just enough power to potentially keep science instruments alive well into the 2030s. If it works, engineers have even hinted that the LECP might be switched back on. They have kept a tiny half-watt motor running on the instrument just in case. The Big Bang is being tested first on Voyager 2, which has slightly more power to spare and is closer to Earth, making it a lower risk candidate. Tests are scheduled for May and June 2026. If those succeed, the same maneuver will be attempted on Voyager 1 no earlier than July 2026. The outcome is not guaranteed. This is a 49-year-old spacecraft running on software that cannot be upgraded, hardware that cannot be replaced, and a power budget so thin that a single unexpected roll maneuver nearly ended the mission. Every command is a gamble. Every response takes a full day to arrive. But NASA is trying, because what Voyager is finding out there is too important to lose. So what is it actually finding? What does interstellar space look like when you measure it directly from inside it, with instruments that no other spacecraft has ever operated in this environment? The answer is strange. The answer is genuinely disturbing in the best scientific sense, because the universe out there does not match our models of what it should look like. Let's start with the boundary itself. For decades, scientists debated where the heliosphere ended. The heliosphere is the enormous bubble of particles and magnetic field that our sun generates, an invisible protective shell surrounding every planet in the solar system. Astronomers guessed the edge might be close to Jupiter's orbit, then farther, then much farther. Voyager kept flying and kept not finding it. Eventually, both probes crossed the boundary, called the heliopause, with Voyager 1 crossing in 2012 and Voyager 2 crossing in 2018. What they measured at that boundary was not at all what scientists expected. First, the temperature. As each spacecraft passed through the heliopause, they recorded the plasma on the outer edge, running at temperatures between 30,000 and 50,000 Kelvin. That is scorching, far hotter than the space inside the sun's magnetic reach. A thermal wall at the edge of our solar system, burning at tens of thousands of degrees, sitting in a region with so few particles that the heat cannot actually damage anything because there is almost nothing there to carry it. But a wall of plasma that hot at the boundary of our solar system was not predicted. Nobody put a 50,000 Kelvin barrier in the models. It is there. Both spacecraft measured it independently. It is real, and we do not fully understand why. There's also the matter of cosmic rays. Inside our heliosphere, the sun's magnetic field acts as a partial shield, deflecting many of the high-energy particles that pour in from across the galaxy. Cosmic rays, particles traveling at nearly the speed of light, are present everywhere in interstellar space, but they are somewhat reduced inside the protective bubble our sun creates. When Voyager 1 crossed the heliopause in 2012, its cosmic ray instruments recorded a dramatic, nearly instantaneous surge in the number of high-energy particles hitting the spacecraft. The count jumped sharply as the probe left the sun's protection behind. This was expected. What was not fully expected was the sheer intensity of the galactic cosmic ray environment right outside the heliopause. Voyager is now operating in a region where it is being continuously bombarded by radiation from across the entire galaxy. Particles that have traveled millions of light years before striking a tiny machine from Earth. The spacecraft was designed to handle radiation. It has survived nearly 50 years of it. But the galactic cosmic ray environment in interstellar space is meaningfully more intense than scientists had estimated based on indirect measurements from inside the solar bubble. The universe beyond the heliosphere is a harder, more energetic, more hostile environment than the space we are used to living in. Our sun has been quietly shielding us from most of it our entire lives, and we only fully grasped the scale of that protection when Voyager stepped outside and measured what was there. Second, the density. When Voyager 2 crossed the heliopause and entered true interstellar space, scientists were surprised to find the plasma on the interstellar side running at roughly twice the temperature they had predicted. The very local interstellar medium, the region just outside our solar bubble, is hotter and denser than the model said it should be. And here is where it gets even stranger. As Voyager 1 has pushed deeper and deeper into interstellar space, the plasma density around the spacecraft has not stayed constant. It has been increasing. Year by year, as the probe moves further from the Sun, the interstellar medium is getting denser around it. Between 2013 and 2015, electron density measurements showed a 40-fold increase from the baseline measured just outside the heliopause. 40 times denser, not gradually, sharply. Voyager is plowing deeper into a region of space that is getting more crowded with particles the further it goes. Scientists have two main theories for why this is happening. One says the interstellar particles are slowing down as they approach the heliopause, stacking up like rush hour traffic at a bottleneck, and Voyager is now driving through the traffic jam. The other theory says the interstellar magnetic field, as it compresses against the edge of our solar bubble, forces charged particles away from the boundary region and toward the surrounding medium, creating a depleted zone just outside the heliopause and a denser zone further out. Voyager may be entering that denser zone right now. The measurements will help determine which theory is correct. But the data itself, the steady increase in density that nobody predicted, is already forcing scientists to revise what they thought they knew about the space between stars. Third, and perhaps most arresting, is the sound, or rather what functions as sound in a region where no human ear could ever survive. In interstellar space, plasma, the ionized gas that fills the void between stars, can carry waves. Pressure waves, oscillations. The same physics that makes sound travel through air also works in plasma, just at far lower densities and far lower frequencies. When Voyager 1's plasma wave subsystem, essentially a pair of 30-foot antennas trailing behind the spacecraft, detected a continuous, persistent hum resonating in the interstellar medium, the scientific community paid immediate attention. Before this discovery, astronomers had detected brief, sharp whistles in the Voyager data, loud bursts of plasma wave activity triggered by solar eruptions, sending shock waves outward through the heliosphere. These bursts were useful. They gave scientists a window into the density of the interstellar medium whenever the Sun fired off an event powerful enough to send ripples all the way to Voyager's location more than 14 billion miles away. But these bursts were like camera flashes. Bright for a moment, then gone. What scientists really needed was a continuous light, and that is what the hum turned out to be. A steady, persistent plasma wave emission resonating at around 3 kilohertz, ongoing regardless of solar activity, providing a continuous window into the density of the space surrounding Voyager. Stella Acker, a researcher at Cornell University who was part of the team that identified this signal, described it as something that would sound like a single steady note played constantly but changing very slightly over time. Not a random noise, not equipment malfunction. A genuine, persistent vibration of the interstellar medium itself, allowing scientists for the first time to measure the density of the space between stars on a continuous basis rather than waiting for the Sun to cooperate. This discovery changed how astronomers can study the interstellar medium. It is the difference between reading a river by watching occasional raindrops and being able to dip your hand in directly. And now the other instrument still running on Voyager 1, the magnetometer, is adding another layer to the picture. The interstellar magnetic field, the weak but real magnetic presence that permeates the space between stars, was measured by Voyager 2 at around 7 microgauss when it crossed the heliopause. That is 64,000 times weaker than Earth's magnetic field, but it is still there. And it is stronger than astronomers predicted. That extra strength, that unexpected pressure from the interstellar magnetic field, is part of why the heliosphere did not behave the way scientists expected during different periods of the Sun's activity cycle. The Sun goes through an 11-year cycle of high and low activity. During peak activity, with more solar wind pouring outward, scientists expected the heliosphere to inflate, pushing the boundary further out. During quiet periods, it should deflate and pull back. When Voyager 1 crossed the heliopause in 2012 and Voyager 2 crossed in 2018, during a period of higher solar activity, astronomers expected to measure a larger heliosphere. They did not. Both spacecraft measured the boundary at almost the same distance. The heliosphere had barely changed. The reason, scientists concluded, was the interstellar magnetic field pushing back with more force than expected, holding the bubble at a roughly constant size regardless of what the Sun was doing. Our solar system's protective shell is being squeezed from the outside, and the squeeze is stronger than anyone knew. All of this is being measured by two machines that were designed not to fail, in the words of former Voyager project manager John Cassani, but were never supposed to last this long. Today, in 2026, Voyager 1 has only 2 active science instruments remaining: the plasma wave subsystem listening for density, changes in the interstellar medium, and the magnetometer measuring its magnetic field. Voyager 2 has 3: These few instruments, running on less than half their original power, communicating across a distance so vast that commands take a full day to arrive, are the only objects humanity has ever placed in direct contact with the interstellar medium. Everything else we know about the space between stars comes from indirect measurements, from telescopes looking in from the inside of our solar bubble. Only Voyager is actually there, only Voyager is touching it, and what it is touching is weirder, hotter, denser, and louder than our models predicted. There is a new spacecraft now, launched in 2025, called the Interstellar Mapping and Acceleration Probe, or IMAP. Scientists describe it as Voyager's data taken to a completely new level of detail, measuring the boundary of the heliosphere with far greater resolution than anything before it. IMAP orbits a stable point about 1 million miles toward the Sun from Earth, building global maps of how the heliosphere interacts with the interstellar medium. Its data, combined with what Voyager is still sending back, is creating the most detailed picture ever assembled of the bubble our solar system lives inside. And every new image that picture produces raises new questions. The heliosphere is not the smooth, spherical bubble that textbooks once showed. It is asymmetric, shaped by the direction of the interstellar magnetic field pressing against it, elongated on one side, compressed on the other. Our sun is moving through the interstellar medium at about 56,000 miles per hour, plowing through a region of space that is actively pushing back. Voyager is in the wake of that plow, measuring the churned-up environment left behind as our solar system cuts through the galaxy. The Big Bang maneuver, whenever it happens, will determine how much more of this territory Voyager gets to map before the silence comes. Engineers are hopeful. The same people who built these spacecraft to last 5 years and watched them run for nearly 5 decades are not people who give up easily. If the Big Bang works on Voyager 2 this summer and then on Voyager 1 in the second half of 2026, there is a real chance that both probes could keep transmitting science data into the 2030s. If it fails, the mission could end within a few years. Either way, the clock is running. And the universe out there, the one that is hotter than expected and denser than expected and louder than expected, is not waiting for us to catch up with it. What is particularly striking about Voyager's situation in 2026 is that the most critical discoveries are being made with the weakest, most depleted version of the mission that has ever existed. At the beginning, the probes had 10 instruments each: cameras, spectrometers, particle detectors, magnetometers, plasma analyzers, the full suite of tools a spacecraft needs to explore a completely unknown environment. As the decades passed and the power declined, instruments were turned off one by one. The cameras went first because there was nothing visible to photograph in the featureless darkness of interstellar space, then the ultraviolet spectrometer, then others. Each shutdown was a quiet funeral for another piece of scientific capability. And yet, somehow, the instruments that remain, the ones measuring plasma waves and magnetic fields, the ones that directly sample the texture and behavior of the interstellar medium itself, turn out to be the most relevant instruments for the questions Voyager is now uniquely positioned to answer. It is as if the mission knew which tools it would need at the end, kept them alive, and is now using them at exactly the right moment to answer questions that did not even exist when the probes launched. The hum of the interstellar medium, the rising density of the space between stars, the hot plasma wall at the edge of our solar system, the uneven, turbulent shape of the heliopause. These are not the discoveries anyone planned for in 1977. They are the discoveries the universe chose to give us, delivered by 2 machines that refuse to die, in a place no one designed them to reach. Consider also what it means that the heliopause itself was not uniform. When Voyager 1 crossed it in 2012 and Voyager 2 crossed it 6 years later in 2018, the 2 probes were traveling in completely different directions, pointing toward different parts of the sky. They are so far apart from each other right now that they are actually farther from each other than either one is from Earth. And yet the 2 boundary crossings were strikingly different from each other. Voyager 1 recorded dramatic fluctuations in the magnetic field at the moment of crossing. Voyager 2 did not see the same magnetic turbulence, but instead detected a thin layer of hot plasma right outside the boundary, a cosmic ray boundary layer that Voyager 1 missed entirely. The heliopause is not a clean, smooth, uniform shell. It is a complicated, turbulent, asymmetric boundary that behaves differently depending on where you cross it and when. Our solar system is not sitting inside a perfectly symmetrical bubble. It is sitting inside a structure that is being pushed and shaped and squeezed by the interstellar environment surrounding it on all sides, and the shape of that squeeze is uneven. The direction of the interstellar magnetic field, the local density of the medium, the motion of our solar system through the galaxy, all of these factors are pressing on the heliosphere from different angles with different forces. Voyager 1 and Voyager 2 gave us 2 data points on that boundary, 2 measurements at 2 different locations, years apart. And even from just 2 data points, the picture that emerged was more complex than anyone had modeled. Imagine what we do not yet know about the other 2/3 of the boundary that no spacecraft has ever measured. Here is what strikes me most deeply about all of this. We are in the extraordinary position of having 2 machines, launched before personal computers existed, before the internet existed, before most of the people watching this video were born, that are right now, today, in 2026, touching territory that no other human creation has ever reached. They are measuring a place that our best scientific models got wrong in multiple significant ways. The heliosphere is not the size we thought. The boundary is not the temperature we predicted. The interstellar magnetic field is not as weak as we assumed. The density of the medium beyond our solar system is increasing in ways our theories struggle to explain. And running through all of it, steady and persistent, is a hum. A real, measurable, continuous vibration of the plasma between the stars, carrying information about a universe we are only just beginning to learn to read. Every day those 2 probes keep operating as another day of data from a place that no mission currently planned will reach again for decades. The next purpose-built interstellar probe, if it is ever funded and launched, would take at least 15 years just to reach where Voyager 1 is now, and much longer to push past it. For now, Voyager is the only voice we have from the space between stars, and that voice is saying things that are genuinely changing what we understand about where we live and what surrounds us on every side, across hundreds of trillions of miles in every direction. The universe beyond our sun is not empty. It is not silent. And it is not what we thought it was. Subscribe right now so you never miss what the universe reveals next. Share this video if you think these discoveries deserve far more attention than they are getting, and drop your questions below, because Voyager's story, even at 49 years old and 16 billion miles from home, is nowhere near over.